Rectifier type instruments. Rectifier type instruments are instruments to measure the AC voltage or AC currents with the help of a rectifier. If the AC instrument uses a rectifier, then we call a rectifier type instrument. In this rectifier type instruments, we can design voltmeters, ammeters, or multimeters. These instruments are used to measure the voltages, currents, or voltage or current. So here we can use a rectifier which may be a half-wave rectifier or a full-wave rectifier. This rectifying device in the rectifier instrument converts the alternating current or voltage to direct current or voltage, and this is given to a meter which responds to the DC values. The most common type of the DC meter is the permanent magnet moving coil meter, which is called as G-Arcelor moment. It is used as the indicating meter. So when we use a half-wave rectifier, as we know, we will be using two diodes in the circuit to convert it into from AC to DC, and if we use a full wave rectifier, we'll be using four diodes either in the bridge form or in the conventional. Here, this is the circuit which is using a half wave rectifier to convert the incoming AC signal to the DC signal. This is a multi-range voltmeter. We have the range selector to select the different ranges connected to R1, R2 or R3, and these resistors R1, R2, R3, as we know, those are the multiplier resistances which are connected to the diode D1, meter and the shunt resistance. These multiplier resistors are used for limiting the value of current so that their value does not extend or exceed more than the rating of the PMMC instrument. Here, in this circuit, the diodes may be made up of elements like germanium or silicon. We already know the working of a diode. It offers zero resistance when it is forward biased, and it offers infinite resistance when it is reverse biased. In this type of rectifier type voltmeter, as you see in the circuit, R1, R2, R3 are in series through the switch. D1 is connected in series with the meter. D2 is connected in series in shunt with the meter. So R shunt is connected in shunt with the PMMC meter. Already we have seen that the diode D1, when we connect this voltmeter across any circuit to measure the AC voltages, diode D1 conducts during the positive half cycles of the incoming signal, and during the negative half cycle D2 conducts. So here the meter shows the average value of the AC signal which we have connected across, but it is calibrated in terms of the RMS value. It gives the readings in terms of RMS values. Here in this circuit, the D1 is conducting when it is forward biased, that is during the positive half cycles, and D2 conducts during the negative half cycles of the input signal. Here diode D1 sees that, diode D2, it conducts during negative half cycles, and it sees that it prevents any flow of any reverse leakage current to diode D1. Hence, it protects the meter against any reverse voltages. This rectifier type of voltmeter, when we use a half-wave rectifier in this circuit, then its sensitivity is only 0.45 times the DC voltmeter, and if you use a full wave rectifier, its sensitivity is only 90% of the DC voltmeter. You can see the waveforms, output waveforms of the voltmeter when we use a half-wave rectifier. Next, in this circuit, we are using a full wave bridge rectifier. As we know, we use a current transformer which couples the AC signal to the bridge rectifier. Here we are using 4 diodes, as we know, D1, D2, D3 and D4. When we connect this full wave bridge rectifier across the circuit to measure the voltage, for positive half cycles of the input voltage, diodes D1 and D4 conducts and current flows through the circuit. For negative half cycles of the input voltage, diodes D2 and D3 conducts and current flows through the circuit. Hence, the resulting output waveform is a pure series of positive half cycles. So this is how a full wave rectifier type voltmeter works. The main advantages of a full wave rectifier type voltmeter is it can be used from frequencies starting from 20 Hz to a high frequency range. And one more thing is it has a uniform scale, it has a good accuracy, and the cost is comparatively low. If you think about the disadvantages of this instrument, the disadvantages of this rectifier type voltmeter is it is less sensitive compared to a DC voltmeter. Hence, the loading effect is high. Coming to the applications of rectifier type voltmeter, this rectifier type voltmeter can be used to measure the voltages ranging from 50 volts to 250 volts. It is generally used in the communication circuits where, as I told you, the loading effect is not so important. Thank you. A ohmmeter. Ohmmeter is one which measures the resistance in a circuit, and also we can check the continuity in a circuit. We have these ohmmeters to be portable, and we have 3 types: the series type ohmmeter, the shunt type ohmmeter, and a multi-range ohmmeter. This is the circuit of a series type ohmmeter. In this series type ohmmeter, we have a d-orthogonal moment which is connected in series with the resistor R1 and a battery E which is connected to a pair of terminals A and B. Across this pair of terminals A and B, we connect the unknown resistance whose value is to be measured. So this forms the basic series type ohmmeter. So the current flowing through this PMMC basic meter depends upon the magnitude of the unknown resistance value Rx connected in the circuit. So the meter deflection is proportional to the value of this unknown resistance Rx. Here in the circuit, we have the current limiting resistor R1, we have the meter, PMMC meter with internal resistance Rm, we have the battery E connected in series to the circuit, and Rx is the unknown resistance to be measured, and R2, it is a zero adjusting resistor. To start with, the design of the series type ohmmeter, we have to calculate the values of R1 and R2 to be connected in this circuit. Supposing the unknown resistance value Rx is 0, that is, if terminals A and B are shorted, then what happens is the maximum current flows in the circuit. So, the meter scale shows the full scale deflection IFSD. If the meter is not showing the full scale, then we can adjust the resistor R2 so that the meter shows the full scale current. So this is marked as IFSG, and this position in the meter is marked as 0 ohms on the scale of the PMMC meter. Next, if Rx is infinity, that is, if terminals A and B are kept open, then the current in the circuit is 0. The meter shows 0 current through it. So here, that is marked as infinity on the scale. So when the unknown resistance is 0, maximum current is flowing through the circuit, and on the meter, the full scale deflection is marked as 0 ohms. When A and B are kept open, that is of infinity resistance, then no current flows through the meter. That is marked as infinity on the meter scale. So in this series type of ohmmeter, on the scale, the rightmost division is 0 and the leftmost division is infinity. And the intermediate markings, that is, the different markings on the scale from 0 to infinity, are marked by connecting the different values of resistors, unknown resistors, and then the meter is calibrated accordingly. Supposing the Rx causes half-scale deflection of the meter. This half-scale deflection means that the current through the unknown resistor and current through the remaining circuit is half. Means RH is the resistance across terminals A and B, which shows half-scale deflection in the meter. So IFSD is a full-scale current, RM is the internal resistance, E is the battery voltage. Now we have to find out the values of R1 and R2 for designing the series type ohmmeter. As I told you, when the unknown resistance is equal to the internal resistance of the circuit, then only the current through the meter is half of the IFSD. Therefore, RH will be equal to, now R2 RM are in shunt. So, R2 RM by R2 plus RM plus R1 is RH. The total resistance presented to the battery equals 2H, 2RH. The unknown resistance is equal to the internal resistance. So, RH equals to R1 plus R2 RM by R2 plus RM. The total resistance in the circuit is 2 times RH. Now, the battery current needed to supply this half-scale deflection is IH, given by E by 2 RH. So, to produce full-scale deflection, the battery current must be doubled, and therefore the total current IT is equal to 2 times IH, which is given as equal to E by RH. Now, the current through R2 is nothing but I2, given as the total current IT minus the meter current, that is IFSD. So, I2 is equal to IT minus IFSG. Now the voltage across the moment and the voltage across the unknown resistor is equal. So ESH is equal to EM, or I2R2 equals to IFSG RM, and R2 which is equal to IFSG IM by I2. So R2 will be given as IFSG RM RH by E minus IFSG RH. So now equation 1 gives the value for R1, and R1 is equal to RH minus R2 RM by R2 plus R. So now you substitute the equation 6 into 7, we get R1 as RH minus IFSG RM RH by E. So here, this is how we find out the values of R1 and R2, and we connect these values in the series type ohmmeter circuit. Thank you. Shunt type ohmmeter. Shunt type ohmmeter is one in which the unknown resistance R, that is, the resistance value to be measured, is connected in parallel with the battery. This is generally used for measurement of low resistance value. The circuit of the shunt type ohmmeter as shown in this figure. We have a battery E connected in series with a variable resistor R1, adjustable resistor, and a meter, PMMC meter, whose internal resistance with RM is connected through a switch, and the terminals AB across which we are going to connect the unknown resistance Rx, whose value is to be measured. The switch is provided here because when not in use, it should not drain away the supply battery. In this shunt type of ohmmeter, as I told you, we have an adjustable resistor R1, the diagonal moment, and the unknown resistance connected across the terminals A and B. When the unknown resistor Rx is 0 ohms, that is, when A and B are shorted, then the meter current is 0. Next, if the unknown resistor value Rx is infinity, that is, when terminals A and B are kept open, then there is no current through the terminals A and B. Maximum current or the full scale current flows through the PMMC meter. Hence, the 0 is marked at the left end of the scale and infinity is marked at the right end of the scale. So when the unknown resistor is of 0 value, it is the indicator shows 0, which is marked on the left side of the scale, and when the resistance is infinity, it shows infinity on this calibrated scale, which is at the right side of the scale. As I told you, this is generally used to measure low value resistors. Here, when Rx is infinity, the full scale meter reading IFSG is given as E by R1 plus Rm, where E is the internal battery voltage, R1 is the current limiting resistor, Rm is the internal resistance of the moment. While designing the shunt ohmmeter, we have to calculate the value of R1. So when Rx is 0, unknown resistor is 0 value, the current Im is 0. When Rx is infinity, by setting R1, the pointer can be made to show the full scale reading, which is IFSG on the meter. Here, R1 is then given as E by IFSG minus Rm. Now, for values in between 0 and infinity, that is when Rx is less than infinity, then the meter current will reduce. Using current division principle of calculating the current through the meter, it is given as Rx by Rx plus Rm into IT, where IT is the total current in the circuit given as E by R1 plus Rx Rm by Rx plus Rm. Im is given as Rx by R1 Rm plus Rx into R1 plus Rm into E. At half scale reading of the meter, zero point 0.5 IFST is given as ERH by R1 Rm plus RH into R1 plus Rm. So when we solve for RH, we get it as R1 Rm by R1 plus Rm. So this is how we calculate the value of R1 to design the shunt ohmmeter, and we calculate the value of RH for half scale deflection, and for different values of resistors connected we find out the value of our resistance and do the calibration of the scale on the ohmmeter. Now just let us see an example. The circuit in the figure uses a 10 milliamp basic diagonal moment with internal resistance of 5 ohms, the battery voltage 3 volts, and the circuit can be modified by adding a current resistor RSH across the moment, and the instrument will indicate 0.5. We have to calculate the value of RSH. We have to calculate the value of the current limiting resistor. So for half scale deflection of the moment, Im equals to 0.5 IFSD, which is nothing but 5 milliamps. Now the voltage across the moment is Em is equal to 5 milliamps into 5 ohms, nothing but 25 milliamps. This voltage appears across the unknown resistor Rx, and the current through the unknown resistor is given as Ix equals to 25 millivolts by 0.5 ohms, which is nothing but 50 milliamps. Now, the current through the moment Im plus the current through the shunt Ish must be equal to the current through the unknown resistor Ix. So Ih equals to Ix minus Im, which is equal to 50 minus 5, which is 45 milliamps. The shunt resistance is then calculated as Em by Ish equals to 25 millivolts divided by 45 milliamps is 5 by 9 ohms. Now, the total battery current is given as IT equals to Im plus Ish plus Ix, which is nothing but 5 plus 45 plus 50 as 100 milliamps. The voltage drop across the limiting resistor R1 equals to 3 volts minus 25 millivolts, which is nothing but 2.975 volts. Here, R1 will be calculated as 2.975 by 100 milliamps equals to 29.75 milliamps. So we have seen what a shunt type ohmmeter is and how to design a shunt type ohmmeter by calculating the value of R1. So this is about series ohmmeter and the shunt ohmmeter. Thank you. Now let us see what is voltmeter sensitivity. When selecting a meter for a certain voltage measurement, it is important to consider the sensitivity of a DC voltmeter. A low sensitivity meter may give a correct reading when measuring voltages in a low resistance circuit, but it is certain to produce unreliable readings in a high resistance circuit. A voltmeter is always connected in parallel across the circuit where the voltage is to be measured. So sensitivity of a voltmeter is defined as the amount of resistance offered by a voltmeter per 1 volt of measurement. It is the ratio of meter resistance Rm and the series resistance Rs to full scale deflection V in volts. The sensitivity is given as Rm plus Rs by V ohms per volt, which is expressed as ohm per volt. Sensitivity is nothing but equal to ohms per volt, which is given as 1 by volts per ohms, which is nothing but 1 by the current. Voltmeter connected across 2 points in a highly resistive circuit acts as a shunt that reduces the equivalent resistance. The meter will give a lower indication than the actual value. This is known as the loading effect. Supposing I have connected a 100 ohm resistor in shunt with 10 kilo ohms resistor. The overall resistance will be equal to 100 into 10k by 100 plus 10k, which gives you 99.009 ohms. Now, supposing I connect a 100 ohm resistor in shunt with 1 kilo ohms resistor, then the equivalent resistance will be 100 into 1k by 100 plus 1k, which is equal to 90.9 ohms. So now you can see the difference when a high resistance is connected in shunt with another resistance. The overall resistance will not be much reduced. But if you connect a low resistance in shunt with another low resistance, the overall resistance will be reduced. So if the voltmeter of low sensitivity is connected across any resistor, then the overall resistance of the circuit will reduce and the reading obtained or the reading shown by the voltmeter is not the correct value, it is a lowered value. So this is called as the loading effect. So in general, when the load resistance across which a voltmeter is connected is in comparison with voltmeter internal resistance, then the loading effect is experienced as I explained just now. In other words, the internal resistance of the voltmeter should be as high as possible to avoid the loading effect. Now, the precautions which we have to consider while connecting a voltmeter is we have to observe the correct polarity. The wrong polarity may cause damage to the deflection system. So while connecting, we have to take care of the positive and the negative terminals. Next, always we have to place the voltmeter across, that is in parallel with the component or with the circuit whose voltage is to be measured. As usual, always start with the highest voltage range and then decrease or select the range which is a suitable level. Now, if I take an example of a circuit across which the voltmeter is connected, in this example, I would like to measure the voltage across the 50 kilo ohm resistor. Here, there are two voltmeters available. One voltmeter with a sensitivity of 1 kilo ohm per volt and a second voltmeter with sensitivity of 20 kilo ohm per volt. With both meters being used for a 50 volts range. The applied voltage is, as you see, it is 150 volts. The 100k series resistor with the 50k series resistor. Now I want to calculate the reading with each meter. The error in each reading expressed as a percentage of true value. So this is what we have to calculate. Now, voltage across the 50 kilo ohms resistor, you can find out as 50k by 150k into 150 volts. Actual value is 50 volts is the voltage across the 50 kilo ohms resistor. This is the correct reading, correct value. Now, if I connect a voltmeter, the first voltmeter with 1 kilo ohms per volt sensitivity has a resistance of 50 into 1k equals 50k. If I want to calculate with the first voltmeter, then 50K resistor causes the equivalent parallel resistance to be decreased to 25 kilo ohms. And the total circuit resistance, instead of 150K, it is only 125K. So the potential difference across the combination of the meter and the 50 kilo ohm resistor will be 25K by 125K into 150 volts, which is equal to 30 volts. Now, if I am connecting the voltmeter, second voltmeter with a 20 kilo ohm sensitivity, has a resistance of 50 volts into 20 kilo ohms, which is 1 mega ohms on its 50 volts range. So when this meter is connected across a 50 kilo ohms resistor, the equivalent parallel resistance equals 47.6 ohms, and the total resistance in the circuit is 100K plus 47.6K, which is nothing but 147.6K. So, if you calculate the voltage V2, voltage across the resistor using second voltmeter, that is the reading I am taking as V2, then 47.6 ohms divided by 147.6 ohms into 150 volts is 48.36 volts. Now, you can see how much error is there by using the first voltmeter. Instead of 50 volts, which is the true voltage, the voltage which I obtained by using the first meter is only 30 volts. So 50 volts minus 30 volts, 20 volts is the error. So 20 divided by 50 into 100, the error is 40%. Now, we'll take the second voltmeter. The true voltage is 50 volts. The apparent voltage is, that is the voltage I measured with the second voltmeter, is 48.36 volts divided by 50 volts into 100. We get it as 3.28% error. So, compared to the first voltmeter, the second voltmeter, the error is only 3.28. In addition to the loading effect, let us see what is the need of high input impedance for voltmeters. The input impedance of a voltmeter should be as high as possible to avoid loading effect. At least it should be higher than the impedance of the circuit under measurement. The input impedance is a function of shunt capacitance across the input terminals. The reactance offered by the shunt capacitance is inversely proportional to the frequency. So Xc is inversely proportional to F. Thus, at high frequencies, the reactance is very small. As this is connected across the input, the overall input impedances reduces at high frequencies. So a passive voltage divider probe can be used to reduce the effect of the shunt capacitance. So this is the effect of the input impedance for voltmeters.